we are now moving into section 14.4, looking at the integrated rate laws and how we come to this idea of the first order, second order, and kind of how it all plays out. So if we were to use calculus, which my assumption is that you don't all know calculus, and so we'll just kind of skip past the actual integration portion. But if we were to use calculus to integrate the rate law for a first order process, it gives us this equation. So where we have the natural log of the concentration of substance A at time t divided by the concentration of A at 0, or the initial concentration. It's going to be equal to negative k, or the constant, the rate law constant, times t, or the time that new concentration or the current concentration is. So I kind of described that, but the concentration of A0 is the initial concentration of A, and then the concentration of AT is the concentration of A at whatever time t you want to know in regard to the reaction. So if we move around the equation, kind of move things around, we can get this relationship where the natural log of the concentration of A at time t minus the natural log, anyway, move it around, we shift things around, and if you notice, we move these things around, we end up having a relationship where it's a graphable equation where we have y equals mx plus b, where y is the natural log of the concentration of A at time t, x is time t, and b is the initial concentration, or the natural log of the initial concentration, and where the slope is based on the rate law constant, or k. So this is for first order rate laws. So first order process, you can have this equation. So therefore, if a reaction is first order, if you plot the natural log concentration of A versus time, you're going to get a straight line. So the benefit of this is that you can actually, let's say you don't have great data to figure out if it's first order or second order, like real clean ones, but you could actually do the natural log of the substance over time, and if it ends up being a linear line, you just plot maybe a couple points. If it's linear, then you know when you're, if you want to draw the rate law, then you know that it's going to be a first order. So let me go to this one real quick. So here we have a substance. We've got methyl isonitrile, and then it converts to acetonitrile. So you get kind of this flopping. So consider, so if this is the case of these occurring, you get this data. So as the pressure, over time the pressure decreases, meaning that the CH3NC is going away. Okay, it's turning into the other stuff at this specific temperature. Well, if we take the natural log of that pressure and then graph it versus time, you end up getting a very linear shaped curve. And so that communicates to us first order process. So then you can write, and the k is a negative, it's the negative of the slope. So because the slopes are going to be negative signs, because because you're decaying, you're getting rid of your reactant or reactant materials, you want to change the sign so you get the proper k value. Okay, so for the second order process, it's similar, slightly different though. So in this case, you integrate it, you end up getting an equation where rather than natural log, we get 1 over these values. And so same idea, you would plug in data, you would get a straight line in this case. So in this example, you've got NO2, it's decaying into oxygen and nitrogen monoxide. And so you graph it. If you graph the natural log, it's still got a slope to it. So that's going to communicate to you. So always start with the natural log, taking the quick natural log of the concentrations over time. And if you graph it or get a rough graph and it's linear, great. It's first order, you can move on, write out the rate law. But if that doesn't work, then you're going to want to then do the second order one where it's 1 over those concentrations. So you kind of move forward to the next option. All right, so this also has applications in half-life when we talk about radioactive material decaying over time, right? Usually at a fixed amount. And half-life also can just be related to the half-life of a reaction. You know, at what time do we get rid of half of the material in the container, or you know, whatever's reacting. So if you want to determine like when am I going to consume up half of my reactant or half of my material, you would then use the following equation. So for a first order process, so we move things around in the equation, okay, and what we end up getting is a fixed value. So you get this fixed number, 0.693, divided by K, which is the rate constant for the reaction, is equal to the half-life, the time when half of the material is gone. So in a first order process, it doesn't matter what the starting concentration of the material is. It's just based on what the rate constant is for that reaction, for that process. Now for a second order process, it's a little different. I'll let it kind of break it down. So we move things around, we're going to manipulate things, come on. And so for this one, for a second order, you still have the rate constant involved, but this time the initial concentration of the material is important in determining the half-life, like when is half of it going to be gone. All right, so we're going to stop there. We'll work on some problems tomorrow in class to kind of explore this more, and this stuff makes your brain hurt. So please take some time this evening to read section 14.4 so that you're more prepared for